we have parameterized finally the metric in terms of these objects n, I and n, and the space metric. So these are called ADM variables, ADM parameterization if you want. And with deze Misner. What remains is to compute square root of minus g, which we need to write the boundary term, and that is equal to n times the square root of k, which is the determinant of the space block there. This can be shown as follows. Let us write g mu nu like this. So the first component is n squared minus ni. Here we list all the others. So minus n1, minus n2, minus n3, minus n1, minus n2, minus n3. Then you have minus kij, so that is minus k11, minus k12, minus k13, etc. 2,1 is 1,2, 1,3, minus k22, minus k23, minus k23, minus k33. So let's see what we get when we compute the determinant. We will do it moving along the first column or the first row. So G is the determinant of G mu nu. So we will have G00 times the determinant of the space part and the determinant of the space part is minus the determinant of K. So K will denote the determinant of Kij. Actually, this should be written in the previous slide. Okay. So this is the first contribution. Then we have the second contribution, for example, here, which will be plus n1 times the determinant of this. Okay, so the determinant of this. Now, what is the determinant of that? It's a 3 by 3 matrix, so it is minus n1 times the determinant of this, etc. That's not so difficult to write because that is minus n1 times the determinant of that, but that is a minor. So you might remember that a minor, the determinant of a minor, can be written as the determinant of the whole matrix times the inverse of the missing of the entry. So the component of the inverse matrix with indices corresponding to the indices that are missing in the minor. Don't know how else to say it in a simpler way. Anyway, so that is minus k n1 K1, 1. And when you compute the others, the other three, you will have the same thing. And 2k and the minor will be k2, 1. We can check. So we are computing the determinant of this matrix, of this block. And if we have computed already the first contribution from here, we are at the second contribution. So it should be this thing. And that can be written that way, with a minus, minus, minus that compensate each other. And the third will be the same. Well, then when we go to minus n2 and minus n3, we will basically repeat the story. So we will get something that can be easily written by means of indices. For example, here we have, you see, n1, and in the squared brackets you have minus k, n I, k I1, and when you add the dots, you just have this. So that is what you get. And in the end, remember that Ni with upper indices is raised by means of the inverse matrix K. So this is what we call Nj, which means that the two contributions here cancel out. And so we remain just with what we wanted, minus K n squared. So the square root of minus g is the square root of k n. N is positive, by the way. Why? Remember that n, capital N, is a component of the normal, the only component of the normal vector, and you have to choose the normal that exits the surface. So let's have to keep in mind that we have this kind of picture. So here the normal will have to be oriented like that. In sigma 2 we are basically working now. And correspondingly in sigma 1 and b. So you can choose a definite sign for n, and we assume that it is positive. Yes, so now we can write the boundary term and check that it does what it is supposed to. So let's recall that the extrinsic curvature k mu nu is h mu rho, h nu sigma, del rho n sigma. We prove that it is symmetric, that it is the Lie derivative of the metric with respect to along the normal, and that can also be written in a simpler form like that. Now we define capital K. There are too many K's maybe. to be the trace of the extrinsic curvature. That's it. And then we want to show that the variation of the object we started with, remember we wrote it W lambda, sigma lambda. We will recall what W lambda is because we will need it in a moment. That variation is equal to the variation of this, there is a twice, of this alternative boundary term, which is the square root of k, the trace, capital K, d3x. So remember, sigma 2 basically is space. The surface sigma 2 is space, the entire space. And now it is written as it should in terms of objects that are well defined and transformed correctly on the surface. So this is the analog of the square root of g for the surface, which is space, entire space in this case. Submanifold, yes, let's call it the right way, submanifold, sigma 2. And K is also a scalar in the submanifold. Well, this is not obvious from here, so let's show that it is. Maybe I should have done it here. So that is equal to what? For example, G mu nu, using the second expression there, rho, del rho n nu, or H mu rho del rho n mu. We raised the index. So it's this object. You remember that H is a projector on the submanifold. H with one lower index and one higher index. And this is covariant, which means that here you have to imagine if to make a diffeomorphism, but the surface will stay the same. The surface is fixed. You make a diffeomorphism, changing the metric on the surface. And so how to see it actually? Maybe this needs a supplementary discussion, I guess. Because well, no, this is a scalar. This is a scalar, so that is there's no question about that, because n mu is a vector. This covariant derivative, this is built with g mu nu and vector, so okay, you could could also see it like that. From there is no need to worry too much, actually. Instead, W is not, let's recall what W was. W lambda is still written in a and it will remain written in a non-covariant way, but the point is that the variation of those two terms will be the same. So that is G mu lambda gamma mu nu nu. Okay, now we want to make this variation and check that the two variations are the same. Let's recall what we are dealing with here. We are parameterizing the boundary in some way. And these two surfaces are like space, and the side part is like time. We will prove this identity separately for sigma 1, sigma 2, and b. Actually, we will only do it for sigma 2 because the rest will be totally analogous. So once you know how it works for sigma 2, you will know that it works for the entire boundary. And however, we have to be careful in making the variation. Let's recall what the deal here is. When we have a variational problem with higher derivatives, we have these extra terms from the boundary contributions, which are the variations of the derivatives of the variations of the field calculated at the boundary. And these are there, of course there, because here we have derivatives of the metric, and those involve knowledge about that we cannot provide. So what is the variation? The variation is, so variational problem. On the boundary of the manifold, which is made of sigma 1 union b union sigma 2. That's the boundary. On that, we will have that the metric delta G mu nu is 0, which means delta n is 0, delta n I is 0, delta k ij is 0. Then the normal will be 0. Well, you could say, why should I worry about the normal? The normal is a normal vector, and the manifold does not change when I make a variation. Well, the manifold doesn't change, but the notion of normal depends on the metric itself. So if the metric doesn't change at the boundary, the normal will not change. And even when I raise the index, I need to use the metric. So it's only because the metric doesn't change that I know that those four vectors will not change. And the same for H, because it's built with G mu nu and N. So let's keep that in mind, but we do not know anything about the variation of the derivatives. Or the derivatives of the variations. And those we have to treat, well, we know something actually, now we will see, but so I repeat, those are precisely the terms we have to care about these things. And those that make the variational problem meaningless, and we want to show basically that they are the same here in both cases, and those therefore disappear in the difference. Let me also recall what sigma lambda was. Sigma lambda is the square root of minus g epsilon lambda mu nu rho sigma dx mu dx nu dx rho divided by 3 factorial, and there is no sigma there. So strictly speaking, we know nothing about these derivatives of the variations. Actually, we know something. We know that the derivative of the variation of the normal is proportional to the normal itself. For some proportionality factors C nu, which are functions, C nu. Why is that? The reason is recall that sigma 2 is given by some equation which we wrote in a certain form, chi of x equals 0. And we know that n mu is proportional to the gradient now. On sigma 2 we also have delta n equals 0. That's our variational problem. Our variational problem tells us that on that surface you have that. So remember, if we considered a curve differentiating that a curve on sigma 2, differentiating the equation capital X of small x of tau equals 0 with respect to tau, we obtain that the gradient is orthogonal to every tangent vector on sigma 2. But we can do the same for this thing here. Because you know that for every point on sigma 2, this delta n nu is vanishing. Whatever it is, the function, the delta n nu is a set of 4 arbitrary functions, but they have to vanish there. So if you differentiate them with respect to tau, you still have the same thing. Which means that on sigma 2, this gradient is orthogonal to every tangent vector. But we know that the normal vector is unique up to a proportionality factor. So that means that this is proportional to n with what index? Mu, because that is the index contracted with the index of the tangent vector, since the norm, and that for every nu. There are 4 functions here, vanish on sigma 2, since the normal is unique up to that. Up to a proportionality factor. And so this is powerful because it tells you that many terms will disappear in our variation that we are now going to perform. So this thing is not 0, but it is proportional to the normal itself. So let's compute the variation, which we call it I, the variation of this integral on sigma 2. So again, we do not need to vary small k, because kij, the variation of kij is 0. The variation of the normal is 0. Let's write this more explicitly. That's the integral on sigma 2 d3x, variation of that trace, which we can write in this last form, yes. H mu nu del nu n nu, and the square root of k, small k, can stay outside. We do not need to vary h. We need to vary n, the derivative actually, and the Christoffel symbols, because here there are some Christoffel symbols. So we have the integral of sigma 2 times the variation of del nu and mu. Let's write that derivative explicitly. That is the variation of del, which becomes partial nu n mu plus Christoffel symbols there. And that's why you need that, why you see that this thing is useful, knowing that the derivative of the variation of the normal is proportional. Let's see the indices. The indices are, no, C is mu. Doesn't really matter, but this disappears because since it is proportional to the normal and it is multiplied by h, and h contracted with the normal is 0, you get 0. And the variation of n is 0 on the surface, so you just end with the variation of gamma. So the result is sigma 2 d3x square root of small k h mu nu delta gamma nu rho mu and rho. And actually we need to make h explicit. H is made of two terms, remember. H is made of delta and minus n. So the delta mu nu will give a term like this: delta gamma mu rho and rho. Then there is another term, and nu and rho gamma nu rho nu delta gamma. So this is the expression of this variation. Now we work out another expression of the same variation. And then we combine the two to find a third expression. We start again from this one, but we rewrite it raising one index and lowering there, and repeating the exercise. So I can also be written as the variation of h mu nu del mu n nu. No problem with that. Delta delta h is 0, and so this is again the integral d3x square root of k, h stays out, and then we have the variation. That's explicit. Let's make this explicit. Partial mu and nu minus now gamma mu nu rho and rho. Again, this I shouldn't have written this equal to that. I should have written the delta of this is equal to that. And the same here for the first term. Again, delta partial mu n, so it's, in the end it is correct to leave the red sign there here also, because this derivative is well, you can lower or raise the index mu because its variation is 0. So actually, not quite. Let's say that we can repeat the same argument we found before that led us to conclude this thing. We can repeat it with delta n lower index nu, which is also 0. But I do not see why the coefficient should be this thing with a lower index. So I think that in general, you can have different or totally unrelated coefficients. Right? I do not see why, because there is a partial derivative here that could act on the metric. Doesn't matter. You know that this holds, and so you have a normal contracted with h, and that is what gives 0 again. So integral sigma 2 d3x square root of k, g mu nu is h mu nu is g mu nu gamma mu nu rho n. Okay, the delta acts again only on gamma because there is no delta on n on the surface, sigma 2. We are calculating the integral on the surface, so we do not need anything that is 0 there. And we have n rho with lower indices. Then we have plus n mu, n nu, gamma mu nu rho, n rho. You see that the second term is exactly the same we found previously. And now we can write I as 1/2 of the first plus 1/2 of the second. Because if you take 1/2 of those, the complicated terms disappear, and what you remain are just those two things, and then it will be easy to show that it will be exactly the variation of W. So this is equal to 1/2 integral sigma 2 d3x square root of k. Then you have delta, gamma, mu, rho, and rho minus g mu nu, delta, gamma, mu, rho, and lower index rho. Okay. Now we want to see what this variation of that gives. So the variation of the integral of sigma 2 w lambda sigma lambda. It's the variation of the integral of sigma 2 square root of minus g epsilon lambda mu nu rho dx mu dx nu Ex rho 3 factorial, and W is G mu nu gamma mu nu lambda gamma alpha beta lambda minus G alpha lambda gamma beta beta alpha. Yes. Okay, now, well, we know that sigma 2 is space. So basically, mu nu rho are 1, 2, 3. And lambda is 0. So you can write that as the variation of square root of minus g d3x times the 0th component there. Recall that the square root of minus g is also equal to square root of k times n. And now, let's remember that the normal, we wrote at some point, the normal with lower indices here it is, and lower index mu is this. So you see that here you have n and an index 0. It's like contracting with n lower index mu. That is to say, you can write this as d3x square root of k n some index rho, that's the same thing, mu nu gamma mu nu rho minus g mu rho gamma mu nu nu. But then it is obvious that the variation here only sees the Christoffel symbols because the others don't have any variation on. We are always on sigma 2 here. It's important to write it down because nothing is true otherwise. So you have n g mu nu delta gamma mu nu rho minus g mu rho delta gamma mu mu nu. Let's check if it is the same as I. I is, apart from the factor 1/2, is delta of, apart from factor I and maybe a sign. Let me check the sign here. Yeah, there may be a sign, by the way. Yes, because you see here we have g mu nu delta mu nu rho, and lower index is there. And lower index is there. And here we have an upper index and an upper index with the delta gamma contract. So there is a factor 2 and a sign. As far as the sign is concerned, yes, there was a sign here, actually, because I was here missing a sign. Why? Here there is a minus. Minus, minus, minus. Why? So here we use that mu nu rho is 1, 2, 3, so mu is 0, but remember that epsilon 0, 1, 2, 3 is minus 1. Epsilon 0, 1, 2, 3 is plus 1 with upper indices. Doesn't really matter, because if it were the other way around, we would still get to the point, redefining our boundary term. Important thing is that the boundary term exists, but here with signs you have to be careful. And in the end, we get what we wanted. So the variation of W lambda, sigma lambda, minus 2 square root of k trace of the extrinsic curvature is equal to 0. Okay, let's stop 10 minutes.